Okay, so I think we can slowly start again. And the next speaker is Urbasi Sinha, and she will tell us about the free violation, loophole-free violation of the Leggett-Garg inequalities.
So thank you very much, and thanks Abhishek and others for the invite to this conference. And so very nice pronunciation. So loophole-free violation of the Leggett-Garg inequalities and semi-device independent random number generation. So this is a specific experiment that I will be discussing in this talk. We work with photons, for those of you who are not familiar with us, and we work in all these areas. But today I'm going to focus on one particular experiment and what we have done in that. Am I audible at the back? Yeah, okay. But then having said that, these are our areas which we are not going to talk about. Only the third thing is what you see going to be the focus of today's talk, but we work a lot on different aspects of quantum communications, quantum computing, quantum sensing, as well as precision tests of foundations of quantum mechanics and quantum gravity. So this is our broad focus. So the plan for the talk, I will be talking about the temporal form of the Bell inequalities, which is known as the Leggett-Garg inequality. And then there is another form, which is the Wigner form of the Leggett-Garg. And we will discuss an experiment where we have done a loophole-free violation of this inequality, followed by how we have used this experiment to generate certified randomness from this violation. I was told that David mentioned my randomness generation in his talk as well. So thanks for that. So it's coincidental that I'm talking about this because I never had the time to upload the abstract yet. So it's a mystery what I'm going to talk about, but now it's solved. It's not random anymore. So having said that, you know, we have, there's a second week in which we are talking about quantum at ICTS, obviously, but the first week of this conference. So quantum is everywhere, right? And this is the International Year of Quantum, so on and so forth. But then, of course, the question does remain, what does it mean for you and me as macroscopic objects? You know, we are really large compared to when things would start making sense in the quantum space. Now, we have these quote-unquote weird features in quantum, whether it's superposition, whether it's tunneling, whether it is, you know, entanglement. We don't see this amongst ourselves. We have a little bit of entanglement maybe in thought, but then we don't really see manifestations, right? So question is, quantum makes sense for the micro world, but what about the macro world, which is your world and my world? And this is, of course, a question that has been asked by several, very, very well-known thinkers and doers before, and this has been a question in our minds. Can we test quantum in the macro limit? When we would stop seeing these effects and so on? And so this brings us to, of course, Albert Einstein, and he, was very uncomfortable with this concept of realism, okay, because, realism says that something has a well-defined property, irrespective of whether you're doing a measurement or not. David is looking at this talk, which is nice, but if I look at this, he'll still look at the talk and not at his laptop. That is realism. So his act of looking at my talk is independent of whether I am observing him or not. And this is true. The moon is there when we don't look at it, and so on and so forth. So we are used to this concept. But then, of course, we have qubits, right? And so these qubits, they, of course, much discussed that, they can be in many possible states till they are measured. And so, of course, the whole idea of quantum seems to be a little bit, not a little bit, it definitely has some difference of opinion, let's say, with realism, because, there is no measurement independent property that we talk about in quantum. There are many things possible. When you measure, then you reveal what has to be revealed. And so this is the concept of realism. So, but the question is, does nature differentiate between micro and macro? And this question was asked very, sort of definitely by Sir Anthony Leggett, who, of course, is a Nobel laureate in physics. And so this is the whole, thing which we are very familiar with, this concept of local realism. And then you have these local realist inequalities, famous one being the Bell inequality and so on. And these work more or less for bipartite or multipartite systems. So you have two objects separated from each other, let's say, and then, they violate the Bell inequality, then you disprove local realism. And so many experiments have happened and so on. So this is mostly about bipartite and multipartite. You can have a version in a single particle, but it's not quite going to comment of non-locality, because a single particle cannot be split into two different locations. So then this question comes in, what about a single particle? And what can we say about its realism or its quantumness for that matter? Is there a specific test we can do experimentally or theoretically for that matter, by which we can talk about the quantumness of a single particle? That brings us to macro realism. Okay, and macro realist inequalities which apply to single systems. So now we don't talk about bipartite systems separated by a distance and doing. So what about a single system? And we use the superposition principle in this case. And so, of course, the famous example of the dead and alive cat. And so a single system can be in a macroscopic superposition of, let's say, two states. And the inequalities that we are going to talk about are derived on this sort of a system. So a single system also should have a dedicated way of being tested for its quantumness and, for that matter, the realism itself. And so this is what differentiates between the two scenarios. Okay. So now, of course, the Bell inequalities have been much discussed, and I'm sure this audience is very familiar with the Bell inequalities. But we also know that it is the loophole-free violation of the Bell inequalities which got these three gentlemen, and of course it's an effort which is much larger than them, it's their groups, the Nobel Prize in 2022. And so this was for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So what is so special about loophole-free is the question. And there are several experiments in this. So if you are, for instance, a theorist and you don't really want to go through all the experiments, then you can have a little look at this review thing which I was invited to write, where I summarized all the experiments to a certain extent. And of course, there is a very nice summary on the Nobel Prize webpage. So loophole-free, these are the loophole-free Bell tests. This is the Zeilinger one, which of course led to the part of the prize, and so on. So now, why is a loophole-free test important? Well, a loophole-free test is important because, if you're spending a lot of time and energy in coming up with these inequality violations, if there is an inequality violation that you have come up with in which there is no flaw, then of course, great, because your underlying theory then is sacrosanct, right? So this is a very nice thing, that this is what we say here, that no remaining doubts that the underlying theory is real and complete, and so on and so on. So it's a nice feeling also to do a loophole-free test, but it's not just about a nice feeling and being happy about the underlying theory. That becomes a little bit part theory, part philosophical. It actually gives rise to this whole new way of quantum communication, which is now receiving a huge boost because of these loophole-free experiments. So when we do quantum communication, whether it's quantum key distribution or random number generation, there is always this problem that if there is an eavesdropper, eavesdropper is our problem guy, and so this eavesdropper is has all the capabilities. We say that eavesdropper is omnipresent, has a quantum computer which we also don't have, and so on, can do anything and everything. So if that is true, then he or she can definitely use one of these loopholes to come up with an attack which brings about a lack of security in an otherwise secure communication experiment. And so this is why a loophole-free test is very important, because when it's a loophole-free architecture, then no eavesdropper can actually come in and use that loophole to come up with a fault or a flaw in that implementation. And so this is what it's a very nice thing. Especially students here definitely have a look at this, where they did a very good job of explaining the importance of a loophole-free, which is important not only from the fundamental thing that underlying theory is good, but also from the practical point of view of giving us these unhackable random numbers and quantum key distribution. So fine, so far so good. This is for bipartite and multipartite scenarios we're talking about, but what about a single particle and its equivalent test? So this brings us back to Tony Leggett and Anupam Garg, who came up with the Leggett-Garg inequality, as I mentioned. And this is the experiment I will be talking about, where we performed the first loophole-free experiment for the Leggett-Garg inequalities. Okay. And also show you an example of how we are already using it for random number generation. So now, this is what I said, realism and locality, that gives rise to the Bell inequalities. Here you replace locality with non-invasive measurability, because you can't have the concept of non-locality for a single particle. So you replace that with this concept, which is non-invasive measurability, we'll talk about it, which gives rise to the Leggett-Garg and Leggett-Garg type inequalities. Now, it is the temporal analog of Bell, So essentially, you have time-separated correlation functions, and you measure joint probabilities between events which are separated in time, instead of course, objects which are separated in space. And the notion of realism is invoked in deriving LGI by assuming that at a certain time during its time evolution, a given system is definitely in one of these macroscopically separated available states. That's the macroscopic superposition, which we have to define in such an experiment in the beginning, which we will show. And non-invasive measurability is the hardest concept, because it is assumed which means that in principle it is possible to determine which of the states the system is in without affecting the state itself or the system's subsequent dynamics. So doing a measurement without having any invasiveness is hard. And so, of course, it's nice to assume this. That's the assumption for the Leggett-Garg. Theoretically, it's a fine assumption. But to do the experiment, that is where the challenge begins. Okay? And so original motivation, as I mentioned, was for this macroscopic systems. And so all these experiments and more, where they've increased the size of the particle and tried to see LGI violation when it fails, and so what is the largest size you can reach, and so on. Now we are using it, and people are using it for the quantumness of a single system. So this is the experiment we'll discuss. As I mentioned, it's a loophole-free experiment. It's the first of its kind. It's obviously, yeah, it does the comprehensive refutation of the classical realist worldview. So far, so good. But then also another thing it does, and this will appeal to the people who work in this particularly, that when you violate an inequality, then quantum mechanics may not be the only theory which might match with this violation. There could be other possible theories also. So we have taken quantum mechanics and derived what is the expectation from a quantum mechanical point of view for our experiment, and matched it with the experiment. And in this derivation, we have taken the imperfections also into account. Because any bound is going to change when an experiment happens, because nothing is ideal. And so this non-idealness has been taken into account as well. And this gives us the non-classicality in a new manner. Okay? And so now this is the Leggett-Garg inequality. So essentially, as I mentioned, I don't know why. Yeah, okay. So these are the 3 time scenarios. Okay, and so these are the functions we would measure, which is T1, T2. So the expectation value T1, T2, T2, T3, and T1, T3, and each of them would involve 4 probabilities. Because of course you can have this, that. That is the idea. And T1, T2, T3 are these 3 instances which we have in this evolution. WLGI, I won't talk a lot about it because we will run out of time, but then essentially it's another inequality also from this time condition, but it has only 3 probabilities. This guy has 12, as I mentioned. Each of the terms has 4. This has 3. And why do we do this? Because you see, both of them are necessary but not sufficient conditions of macrorealism. So simultaneous violation provides a more robust violation. That's one thing. And secondly, as an experimentalist, whether you like it or not, we don't like to do more experiments than what is needed, because each experiment adds an error. And so this has 3, that has 12. So naturally, we would expect that it's a more experimentally friendly parameter because it has less number of terms, which is good. And so this is what motivated us. And so, yeah. Okay, so you're going to pause that timer or not? Because I said, or it's more relaxed than that.
Can you come back?
Yeah, please. This one.
The QM bound, it's easy to see.
Can you please repeat that?
The QM bound 1.5 and 0.5, it is easy to see?
It is easy to see. Yes, of course. I mean, not very easy. I mean, it's a calculation, but it is not difficult to see. But the macro-realist bound is 1.
And the classical bound, it is?
The classical bound is the macro-realist bound. We call it the macro-realist bound because a classical and macro-realist.
So it is 1 for the 2?
It is 1. So
yeah, it's 1 in here. Sorry.
It's 1 here.
Okay.
And so between 1 and 1.5, it is not macro-realist. 1.5 is the upper bound. It's like your 2 and 2 root 2 for CHS.
I didn't show the inequality. 1. Okay, perfect. Thanks.
Yeah, great, thank you. So, yeah.
What does it represent actually? Like this T1 and then the blue thing goes up?
Oh, this I will explain through the experiment. The blue thing.
Why does it go up and what does it?
Yeah, the blue thing is a blocker. I will explain that when I discuss the experiment. Yeah. So essentially, these are time instances, Abhishek. So here, I mean, I'm just saying that, there are 2 possibilities for the particle, either up or down, and that is the superposition that it's generated in, right? But of course, at a given instance, it will be either up or down. Likewise, it will be either up or down or up or down. Okay, but this is essentially just to tell you that if I can place a detector here, how will I measure? I mean, that is why, I mean, when following your suggestion, I'm going to go through the experimental schematic.
This is just one of the outcomes.
Yeah. This is just one of the outcomes to see what we mean by 1, 2, and 3 even, right? Okay, so, and so this is even easier now. So this is the schematic of the experiment, okay? And so this is, the state that we have generated. And this state can, of course, once it hits a beam split, it's a single photon, so it can either be transmitted or reflected, right? And so if it is transmitted, it forms the +1 possibility, and if it is reflected, it is -1. That is how you define the dichotomic state, upper and lower path of the interferometer. So this is the creation of the superposition. After that, I have another beam splitter, and of course, I'm doing phase control, which is necessary. So I'm going to create, now this is where I'll have the interference. And that is why I chose to talk on this, because this is quantum trajectories. I thought I should talk about an interference experiment. And so this is, of course, a concatenated interferometer geometry, as you can see. And so this gives rise to the interference term. And so this is your T1, okay, so T2, and T3. And of course, in principle, we should be measuring, T1, T2, we will measure here, T2, T3 here, again, T1, T3 there and that T2 also comes in, and that I will show you how, interestingly, we have done certain things to avoid the T2 measurement. That's a detail. But having said that, one question which should be coming to your mind is, we are talking about a macro-realist experiment. Somebody is... yes, sir, yeah.
So is the length of you're varying T by varying the length?
Oh, yeah. In principle, right? But then, of course, it's a photon, so it's not like we... essentially, these are time instances in the journey of the photon through this concatenated Mach-Zehnder geometry. So this is where the photon would be at time T1.
So even if they were equal, it just be T1 is equal.
Because photon is traveling at a certain...
So T you're starting at this.
Yeah, so this is T0, okay, and T1, T2, T3. So just to tell you how we are doing the joint probability, where the detector will be, because how do we differentiate between? So this is the T1 zone, this is the T2 zone, and the final is the T3 zone. But as I was saying that, we are talking about a photon, which famously doesn't really have a mass. So now this is a macroscopic realism. A question should come to your mind. What do we mean by doing a macro realism experiment using a photon? Because I talked about the mass increasing and all that. But that is the point, right? So macroscopicity is a parameter which is defined in the context of the experiment. And of course, in our case, the macroscopicity parameter is characterized by the ratio of the spatial separation of the two arms of the interferometer to the wavelength of the photon. Now, the wavelength of the photon is 810 nanometer, and this is centimeters. So our macroscopicity parameter actually is 10 to the 4, okay, which is very high. Likewise, for this interesting experiment with which Tony Leggett was himself involved in, they had done this using superconducting, and that's why I'm looking at you, the squid geometry. And so they had done the clockwise and anti-clockwise flux, and taken the ratio of that to be the macroscopicity parameter. So this is a misconception, if there is one, that macroscopicity just is defined by increasing masses. It is about how well you're able to distinguish between the two states of the superposition. And in our case, of course, it's a very fine distinguishing because, it's in centimeters and nanometer. So our macroscopicity parameter is very large, even though it's a single photon. And so this is a subtlety which I thought I should discuss. Someone... You're saying something? Okay, I just thought. Okay, so now negative result measurement means, okay, the loopholes. So I'm going to walk you through the loopholes and how we have, closed these loopholes, which is the main thing. So what is clumsiness loophole? Clumsiness loophole is something which we can do very easily, right? Like doing an experiment leaves some sort of a mark. And I mean, it is a sign of being clumsy. If you are a robot or something doing an experiment, everything is perfect, then nothing like that happens, of course, So there is always this thing that, some invasiveness is there. And of course, that is the premise for LGI derivation, that there is no invasiveness. And that is what brings about this loophole. It's a very natural loophole in LGI experiments, because it's very difficult to not have this loophole, however hard you try. And one of the ways in which many groups have done this is by doing a negative result measurement, okay? What is a negative result measurement? It's a measurement in which the outcome is inferred when the detector is not triggered. Now, What do you mean? So we are detecting, and we are saying, okay, the act of detection will leave some information or whatever. But now I'm saying that, okay, I have an ensemble. On one side I'm detecting, and I don't worry about these particles. I only worry about the particles which don't even get detected. So in principle, that is one way of saying that, okay, I can be, I'm not, that is an ideal way of closing the clumsiness loophole, is what people have been saying, and this is what I mean. Now this picture comes in again, Abhishek. So this is just to give you a sense for where the photon is in the experiment. So maybe this is one example, okay? So now if I'm putting the detector here, then of course, those photons get blocked. But if I have, there are also photons which will be here. So these are not even detected. So if you don't even detect something, you can't be clumsy with it. That is the idea, and that is a negative result measurement. But then comes an obvious question that, how good is your detection? So your detection has a 60 to 70% efficiency, let's say. Any detector will not be 100%. And so obviously some of them will, not contribute. So this is not perfect. It's not it's detected or not detected. Some of them may have intended to be detected, but they weren't detected because of the inefficiency and so on. So what we did is we replaced these detectors with perfect blockers. So we actually created blockers which are 100% efficient. Like, it's a terrible way of detecting something because you can never use it anyway, but we just block it. And so we created these guys, in our workshop and tested them separately, as a result of which, of course, there is more confidence in the NRM. But that's not enough. Any measurements are inherently invasive. So non-idealness of NRM can result in classical disturbance that can lead to a false value. Because you see, even if you try, even this guy is invasive at least on this subset, right? So this amount of invasiveness will affect that ensemble which is not getting detected. And so then we need to come up with something better, and that is what we actually did in our experiment. And this is a bit of a detail, but having said that, we want to do non-invasive measurability, but there's also something called no signaling in time, which is another kind of correlation. This is more an equality than an inequality. And so what that essentially means is the choice of measurement at any instant does not affect the statistical results of any measurement at a later time. So if you now go through this, just go through the first equation, you have this P, T2, okay? So we are saying that the result at T1 can be plus or minus, doesn't matter. My result is, what I measure here will be the sum of these two, because the act of the first thing does not affect the second one. And so this is NSIT, okay? And this is very well known. But what we went on to do is say, okay, that we are doing an experiment in which we are satisfying NSIT and violating LGI. And this is crucial. No other experiment has done that before. So people usually go for LGI violation to prove something or the other, or they do NSIT violation, because NSIT violation is another way of talking about realism. But what we are saying is that we are going to satisfy no signaling in time, which is the statistical way of satisfying NIM, and violate LGI. And we came up with the conditions for that. So this gives us a stronger clumsiness loophole closure than just NRM. So we did NRM and this, yeah. Plus minus is essentially this, yeah.
Is it the polarization?
No, in our case it's position.
The
two branches, upper and lower arm of the interferometer. We are not doing polarization in this experiment. Polarization is there inherently, but it's not a degree of freedom, yeah, for us. Okay. Which branch? And then, of course, not one measurement. We have to make 12 joint probability measurements, as I mentioned. Because, each of these, so as I said, T1, T2, if you think about it, will have possibility for this, that, and that. So we will have to measure all four to talk about the expectation value of T1, T2. Likewise, T2. So there are four hidden terms in each expectation value. And that's why there are 12 for LGI, okay? But then the satisfaction of NSIT is important. I'm not sure anymore about, I hope the chairperson is also relaxed about giving me a bit more time. Okay, yes, Sai.
Sorry, Urbasi, just a quick question, which is in kind of the spatial Bell's inequality tests and so on and so forth, my understanding of it is that it is all about kind of setting the story up as in an antagonistic way, that there is some kind of experimental interference that, And so when people do things like no signaling, so on and so forth, they're always using space-like separated. There's
No
all this
signaling.
there is all
stop.
of this argument about basically
Absolutely.
how you could convince me on the basis of other parts of physical theory that I will
Because no
concede.
signaling cannot be violated.
And,
it's more like a
exactly.
law of nature.
And so what I'm missing here is, what is the antagonistic setup where you're saying, this could happen in my experiment and this is how I'm defending against it? So
no, that's the point. You see, so no signaling in time is not a law of nature. No signaling in time is essentially a condition which we can choose to satisfy. I mean, so the whole idea is that we are saying that any measurement at a later time is not affected by a measurement at an intermediate time. And so now that is what will give rise to those equalities in this case. So it is not like, Bell inequality where we have realism and no signaling and we say, okay, we are violating Bell inequality. We cannot violate no signaling and so we are definitely violating realism. That is where you're saying the antagonistic nature. Yeah. But here we have non-invasive measurability and realism. Realism remains, right? But non-invasive measure. So if you violate Leggett-Garg inequality, you will of course violate both of these assumptions. But now we are saying that we are taking a lot of effort to do an experiment where non-invasive measurability is satisfied. And that is harder because no signaling is satisfied as a law of nature. But here, the non-invasive measurability counterpart of no signaling for LGI derivation is not very easy to satisfy in an experiment. That is what I was saying earlier. So you have to work very hard to ensure that your NIM condition is satisfied well enough that your violation of LGI is actually a violation of realism. And so that is why it makes it a harder problem than, let's say, in a Bell scenario where no signaling.
Usually, I mean, so
you don't have to work hard.
Sorry.
Yeah. You don't have to work hard to, satisfy no signaling.
Usually in the Zeilinger experiment, all of the famous experiments, as far as I understand, the game that they're playing is they're taking the antagonist point of view and disproving the antagonist point of view.
Absolutely. So our antagonist point of view requires.
If you, let's say, have a violation, square root 2, you could, of course, I mean, there are all these games which, where if you have classical random variables, shared random variables, then you can fake, one bit of randomness can fake a Bell's inequality test. So this is the thing that they're defending against. And so here in time, what is this? What is
we are defending, we are saying that we have satisfied NIM just like they are satisfying no signaling, except that their satisfaction of no signaling is easier, not they and us. I mean, Bell inequality experiments are using no signaling and realism as the condition, primary condition. And when they violate Bell inequality, they can claim a little more easily that they are violating local realism, because of course there is the whole idea of non-locality, simply because no signaling does not require any specific ingenuity to satisfy, given that it's so. But here we have the NIM in the same footing as no signaling, but we have to work much harder to satisfy NIM because it's not natural, because NIM means there's no invasiveness, and to do an experiment which really is doesn't suffer from the clumsiness loophole is harder to solve, and so that is why it becomes it's not a law of nature that we can make use of. We have to ensure that yes, this is the reason why we are saying clumsiness loophole is closed. Then of course it's the same thing that okay, this is satisfied, so the other guy has to be this thing. And of course, we have Mahesh here, who is an expert on temporal correlations and these sort of experiments in NMR, right? Okay, so I am going to continue with this. So Sai, good so far? Yeah. Okay, so now, so that was clumsiness. Now we go on to fair sampling loophole or the detection efficiency loophole. Now this one is an easier thing to appreciate. Clumsiness is the hardest one, I think. It took us also a lot of time to figure out what exactly was going on. We are also clumsy, okay? But then the detection efficiency loophole is easy because, no detector is 100% efficient. So what is the conspiracy theory in quantum optics? That, you have a detector and it is detecting 70 out of the 100 photons that are falling on it. You're violating Bell inequality, good. But those other 30 photons that you did not detect might do some, some secret meeting and decide to satisfy Bell inequality. You have no way of, really commenting on their behavior because you didn't even detect them. And so this is a problem, right? And so what do we do? Usually Bell or LGI, what we would do is we will calculate through hidden variable theory, which we have done. Have a look at our paper. It's a very long calculation where we have taken the same approach as Bell and said, okay, what is the critical detection efficiency beyond which I can say that, it is sort of satisfied. I mean, it'll work for me. So for CHSH, it's like a 66, 67% threshold. For LGI and WLGI, it turns out to be this, okay? So we need this sort of a detector, but we didn't have this available with us when we were doing the experiment. So we did something which I think is on hindsight good. Sometimes not having resources is good because it makes you think harder. And so then what we did, and so this is where I was coming to, Abhishek, when you were asking. And so, this, instead of actually putting a detector here, we have put a blocker, as I mentioned. So this blocker is a 100% efficient detector. But then still, the whole idea is we have been able to shift all the detections to T3. So I said, you have T1, T2, T1, T2, T2, T3. So in principle, you would have expected a detection event here. So this is, by using what is called the arrow of time induction equations and the NIM assumption. I can't go through the details of the theory here, but then have a look. We have been able to, so this whole calculation that we did for the hidden variable, we were able to replace that with another calculation where the detection efficiency eta just became a term in the denominator. Everything divided by eta. So anything non-zero is okay. So instead of having 85 or 78 or whatever, something non-zero, then it won't blow up. Otherwise, it's not okay. But non-zero is easy. And so we basically made it irrelevant in our context. And that was actually one of the very nice things on this experiment, that we did not have to close it. We didn't even worry about it because it became any non-zero is okay for us. And this requires more discussion on how, but it's a theory thing. Another loophole is multi-photon emission loophole, and I will not talk a lot about it because it's not very big. This is your LGI and the one, right? And so if you take into consideration the fact that you can have more than one photon at a time in your experiment, which can happen with some very small probability, which we calculated, then this correction term is just 0.0023. So it just changes 1 to 3rd decimal place, so it didn't bother us actually. But we anyway did it and closed this. So this is the actual schematic. Abhishek wanted to understand the schematic. He wrote an email saying, I want to understand experiment schematic. So this is the actual schematic of the experiment, which is very similar to the proposal, of course, that you saw earlier, except that, one important difference is that, okay, so this is where the photon has come out, right? So this is the BBO crystal, out of which I have 2 single photons, literally pair photons. So one of them I am using as the heralding arm, which is a concept maybe you're aware that, I'm using this to know the presence of this guy, okay? So once there is a measurement here, I know that there is another photon, which is its pair, which I don't measure. This goes into my concatenated interferometer geometry. The first one is a Mach-Zehnder, but then, it is, these 2 arms are not the same length. That was done in purpose so that we don't have an interference here. We just wanted to create a superposition of +1 and -1, the possibility of the up and down, okay? Here we have what is called a displaced Sagnac geometry, a little bit detailed. So instead of a Mach-Zehnder, if you actually have a geometry of an interferometer which closes on itself, advantage is that in a Mach-Zehnder what will happen is that you have an arm and another arm, you can have some phase fluctuation affect the individual arms, which will then go and mess up with your interference result. You can have a maxima shift to a little bit as a function of time. But if you have it close on itself, any error in the arm actually affects both the arms. And so it's like, 2 wrongs make a right scenario. And so a displaced Sagnac is a stable geometry for phase stability, which we have used in several other experiments. We also modified the experiment to do this, okay? And then as you can see, there are the 2 T2 and these are the 2 detectors in the end. As I mentioned, we have shifted everything to the end, which in this case is T3. And these are your blockers, okay? They are, of course, they look much better in the lab, but they come in and out. I mean, to create the various conditions of where you want the photon to go through. So 12 different conditions are created this way, okay? And so, and these are the various experiments which close the clumsiness loophole in their own way. But then other loopholes have not garnered that much attention. The detection efficiency loophole, nobody talked about in LGI literature. but it's a critical role in many analysis of Bell, right? And so this is the USP of this experiment, where we actually managed to, close all of them in the same experiment. And this is the result, of course, after all this, for the gentleman in pink in front, this is the macro-realist bound one, yeah? And so we, of course, got this experimentally measured value, which matched very well with the quantum mechanical prediction. And this quantum mechanical prediction has changed now from 1.5 because of the the imperfections of the experiment. So that actually is a huge calculation we had to do. That no beam splitter is 50-50. I mean, many things concatenated change this to this, okay? And then, of course, these are the systematic change, and then you will also have changes due to statistical, even in your bound calculation. So that is how this ended up. This is our NSIT satisfaction, okay? Because I've finished half, but I will do the other half in less time. Yeah, because it's beautiful. I hope for 10, because you asked too many questions. Yeah, because I've just finished the LGI. I want to tell you about randomness generation, which was what I was trying to motivate. This is the one. This is. Don't ask any questions. Okay, so which is good. So this is the experiment. I mean, so okay. So that was all about the loophole-free violation of the LGI, right? And we saw it was a beautiful violation which matches beautifully with the expectation. That's why it's beautiful. But then, having said that, what do we do with this beautiful violation? We do what we promised, that we are going to use this architecture for secure communication. And the first thing we did is generate random numbers using this violation of the LGI. Okay, and so random numbers, I think you have introduced in your talk. So I think we can all agree that it is important for us. But we can also agree that it is not very easy to generate random numbers in a good way. It's easy to use a MATLAB code to generate random numbers. But what are we talking about here? So understanding is important. So pseudo-random number generators, I mean, I'll skip some math here, which is a way in which my student was generating it using MATLAB. But then essentially the knowledge of the seed gives, it tells you the random sequence. And so the sequence starts repeating either after a long time or very quickly. And so it produces numbers easily. We can use it for our purposes, but the problem is that it's not truly random, and it's predictable enough to be not used in secure cryptography. That is the important thing, which is where we want to be useful. Then there is the true random numbers. Just for my disclaimer, I didn't name these guys this way. Nothing is true about it. Okay, so this is a community which felt that nothing could go beyond true, but now we have beyond truth, which is device independence. So this is not my doing. So true random numbers, it's from an entropy source, okay? These are all examples. Likewise, quantum random number generator is an example of the true random number. The photon on a beam splitter is an example of a true random number, okay? But then the question is, you have an input, you have this sequence. But how do we certify the randomness from the bit string? Once you have this bit string, you take a pseudo, you take a true, you take a beyond true, all of them will satisfy your NIST tests, okay? And those NIST tests really get to us because, they're not really doing anything beyond saying, okay, everything is random. But that's not the point. The point is that now, okay, you will look like an intelligent person. You have this bit string, you copy it on a stick, and then give me the output from that stick. How would I certify the source? There's no way in which I can certify this randomness. I have it, fine, but then I don't know whether there is something going wrong with the source. If the source is decaying with time, we are all aging, source is aging, we have no way of figuring that out, and so on and so forth. So there are many reasons why we need to get independent from the source itself. Okay, and device itself, as we call it. And this was, of course, the first way of doing it, which is using the Bell inequality violation. And this is the first, approach which has been followed over the last few years for this method. Now, Bell inequalities, I will skip. You all know what it is by now, and we discussed Sai and I had a wonderful conversation. And so this is how you derive Bell inequality. And I will skip the details of Bell. Now, randomness from Bell is interesting, and then I forgot to put the references here. So Nicolas Gisin first suggested that this is possible, but then Howard Wiseman, who has probably not yet appeared in this conference with Eric Cavalcanti, they wrote a beautiful paper actually, where they showed that you can have an alternative derivation by using predictability and no signaling. Now, this is important for Psi. and others. But then this is the point. So just not about, no signaling and locality, but then you can replace this with these two conditions and it works beautifully. So now this can be used, and I mean, I'll skip the derivation, but then essentially if you now violate Bell inequality, as we discussed, we will violate these two, but then you can't violate no signaling. So you violate predictability, which means you're generating random numbers. So this was the general idea. And these are the various papers which have done this, okay? But one of the things which we have somehow discussed is, this part is easy because we've discussed so much about it, that, these two parties, they are separated from each other and they need to be far enough apart so that they're not inside each other's light cone and so on and so forth. Otherwise, you won't have a loophole-free experiment. So we know from all these papers and many more that in order to do that, with current, speed of operations that we have, with electronics and otherwise, we will require a separation at least 187 to 200 meters is where we are right now. And so these experiments have all used that to generate random numbers. Not the first few, they didn't bother about loophole free and then the loophole free. But now you see where our experiment comes in, because if we use an alternative inequality to generate where the separation doesn't even play a role, I have a single particle moving ahead in time, the separation becomes irrelevant. So if I can use now this to generate randomness by using a similar argument to the Bell, that actually may lead to a device which will be even portable in future. A 200-meter portable device is a little bit futuristic, right? And so this is the whole idea. And now temporal, I can very nicely skip this because we know all this very well now. So it's just a bit of a revision. So this is the thing. So now instead of predictability and no signaling, I will have predictability and no signaling in time to derive Leggett-Garg inequality. And so this is something, again, I will skip. You can see this paper. It has a lot more detail than I can cover right now. But having said that, when I do that, you can see the argument very easily. I hope that no signaling in time is what we are satisfying in the experiment. And so this is why our experiment is very special, because we are doing an experiment where we are satisfying no signaling in time and violating LGI. And that's the perfect way in which I can use that experiment to violate predictability. Okay, and this is what we did. Now I'll skip the math here. We did the analytic way of generating this. So have a look at the paper is something I'll keep saying now. But then essentially, we generated the analytic bound as well. And these are the assumptions. It's important for those who are experts in this topic that, we have 3 assumptions in this. That is why we call it a semi-device independent. Because we want to go to a stage where we don't have these assumptions, but at the moment, these assumptions are there, okay? And so that is what it is. And this is the bound. As I said, essentially, this is the genuine randomness as a function of the violation. So 1 to 1.5, right? And so at 1.5, you will have 1.4 bits, which is very nice, actually. So this is the theoretical understanding. We also did a lot of analysis of security against state preparation, using, assuming an eavesdropper is existing, what would happen? And so the bound with secure state pressure, it goes down, but then obviously it's still very non-zero. Likewise, we also weaken the NSIT conditions. How do you know it's 0? How do you know you're satisfying it completely? So we actually went with different, possible violations of this NSIT condition and still calculated appreciable randomness. This is all the theory part. We also took into account the memory effect, which is a very crucial thing. If you see the Pironio paper from on the Bell part, okay? So each run might not be independent. So we calculated the memory effect and saw the bound on, what happens to it in the presence of the memory effect. Okay, and so the experiment you have just seen. So I will not talk about exactly what the experiment is, because I hope by now you have an idea. So these are the various correlations which we are measuring, as you know. And so I just want to go to the results because we're running out of time. Blockers are 100% efficient. So we have conducted 1,000 runs of the experiment, just for your knowledge. Sub-experiments were selected at random for each run so that there is no bias. This was the violation. This is the quantum mechanical one. These are the NSIT satisfactions. And the random bits were generated from, these are the actual results. So these are the bits that we generated for each of these experiments, okay, which gives rise to the bit string, the random bit string. Okay, and so I don't know why it flies in, but these are the number of bits we were able to generate. And this was the rate. So this is, of course, going to improve, hopefully with time, with better sources and so on. But it's around 1 million bits, and it's much more appreciable than the initial Bell ones for sure, and with the advantage that it's loophole free. Okay, and so conclusion, great. So semi-device independent generation of random numbers using temporal correlations doesn't require this large spatial separation and preservation of entanglement over distance, doesn't require entanglement. Loophole-free experiment is at an appreciable rate. It's secure against the attacks on the initial state, and it's a rigorous estimation, taking into account the possible side information available to the adversary, employing extraction and amplification. This will be done in future. That is what we hope. We are going to take this to extraction and amplification and so on, like the bell. So this is us with Tony Leggett celebrating his birthday, but also showing us, him his experiment, not his experiment on LGI. And a little bit, I want to say that New Scientists did call us the most watertight experiment of all time. So definitely some appreciation there. With that, I will thank you for your attention and ask you to join our lab to know more details about all these experiments.
Thank you for this very nice talk.
I don't know about time anymore. We are correlated in time. Yeah.
So we already had many questions during the talk, but if there is...
Prabha is raising hand
should be
without a mic.
Can you hear me? Yeah.
Yes.
Okay, so just one question. It was a detail in one of the slides which you had to go through very fast because of lack of time. So the projective measurement that you're performing, if I understand, is the information about the path of the photon. It's about or the presence or absence of a photon in a path. But you also said you do a POVM in the random number generator experiment.
No, the last experiment is, of course, a coincidence detection. So it is not just about the absence or the presence, because in the middle we are talking about the upper path and lower path, but in the end it is a coincidence detection. So it is not quite a projective measurement. So it could be more generalized than that. Is where we are right now. So we are saying it's not a projective measurement because it's not just about upper path or lower path. So in the T1, upper path, lower path, T2, upper path, lower path, T3, you may appreciate, is not just about upper path, lower path. It's the result of the interference. Okay. And so the result of the interference is a coincidence between that detection and the heralded arm. And so that is why it's not a projective measurement. But ultimately, we would like to go to a scenario where everything is more generalized, which it isn't right now.
I see. Okay. Yeah. Thanks.
Right.
So if there are no other questions, I suggest that we move on.
Sure. Thank you very much.